So in Module 1, we sort of glossed over where the weak form actually comes from. Well, we need to think about it in terms of how the approximate solution satisfies the original PDE. In general, the approximate solution won't perfectly satisfy the PDE, and so what happens is we'll be left with, rather than some value 0, we'll be left with some sort of residual. So we need to think about how we'd like to look at what the best approximation is. So one approach would be to think about how could we keep the residual as small as possible. So one approach would be to take a projection of the residual on some vector space. So in this sense, a projection finds the closest fit on a particular vector space compared to the original. So an orthogonal projection does just this. So you can imagine you have a underlying geometric analog. So imagine you have some three-dimensional vector here. You can project it on a two-dimensional space such that this point here, which is the true point, the closest you can get to that point in the two-dimensional plane is this particular point. So this is our orthogonal projection. So in the geometric sense, the orthogonal means that the vector connecting call it the exact point with the approximate point is perpendicular with respect to the space that you're projecting your point on. So we can draw the direct analog in terms of the more generalized vector space, where we can imagine we have some particular function, and we, in some particular space, and this is potentially the exact solution, and we restrict ourselves to only allowing approximate function spaces. So when we do this, we project it on our approximate function space, and doing so as an orthogonal projection means that what we get for our approximation is the best we could hope to get in that particular approximation space. So the geometric meaning of an orthogonal projection makes sense here. So what is the extension to arbitrary general vector spaces? Well, you may recall that the inner product in a function space is simply the integral of the product of two functions. So this is the inner product of f with g. Now, for a orthogonal projection, what we're saying is that the inner product is equal to 0. So in other words, whenever your inner product is equal to 0, you're saying something about f and g, that they're orthogonal with respect to each other. So if we imagine that instead of two arbitrary functions f and g, we instead say our residual and our function space, so we called it v sub h before, and we had basis functions for our weighting functions in that space. So then for each of our weighting bases j, we should require them to be equal to 0. So in other words, our residual is orthogonal with respect to the bases for our approximation space. So this completes a orthogonal projection. And what this seeks to do is minimize the L2 norm with respect to the space that we're projecting upon. So you notice if we were to replace our expression for our residual here, we would recover the weak form, right? So r is equal to dq dt This is an erroneous term. This shouldn't be here. I apologize. Times our, well, actually, let's put this in parentheses here. So dq dt plus df dx times our weighting basis function. And this has to be equal to 0. And clearly we can see if we expand this out so we get two integrals, we recover our weak form. So really what our weak form is saying then is it's enforcing an orthogonal projection of our approximation onto an approximation space. So this is more or less just restating what we already said here. But notice the projected space doesn't have to be the same space as the solution approximation. If we take the finite element approach and we choose them to be the same, then we get, to be pedantic, the Bubnov-Galerkin approach. However, if we were to choose the two spaces to be different, this would be what's called a Petrov-Galerkin approach. So you could imagine then that your weighting basis functions could be something completely different than what your solution approximation basis functions are. So an example, if you chose a weighted space of delta functions, this would yield what's called the collocation method, where instead of talking about how your solution approximation approximates everywhere in your local element, it would be at a set of discrete points, so the collocated points.